Also for myself. Hopefully this goes on. Okay. I just need to mute it here because otherwise we'll hear it twice. It's a 20-second delay cut, but that's correct. That's
smaller computing devices.
Also for myself. There you go. Now I muted them. It's okay. So now we're on. And I'll just go mute myself here and go ahead and do this. I think you can start in about 1 minute. Okay.
Will do.
Thanks, Matthias.
No worries. Yeah, happy to help. I mean, you do most of the work, so I'm happy to chip in at least every now and then. All right, so like every second someone is now joining, so just give them 30 more seconds and then we'll start. Okay, so I think it's time to start, 3 o'clock German time. So it's my great pleasure to welcome you all to this week's online SPICE-SPIN+X seminar. This series was initiated by Jairo Sinova, and he is usually hosting this as part of the Spintronics Interdisciplinary Center. And this is co-hosted then by the SPIN+X Collaborative Research Center, which is headed by Martin Eschlimann and Burkhard Hillebrand in Kaiserslautern and by myself in Mainz. So as most of you already know, I see a number of familiar names. The talks will be given in Zoom and also live streamed on the SPICE YouTube channel. And as usual, we have a webinar, which means that right now the participants can only listen, but if you have questions, you can put them in the chat, and also you can raise your hand later, and then I, or respectively Karen Ebershaw-Sitte, who is co-hosting the second half of this talk, will then upgrade you to speaker, so you're allowed, you can ask your question. The talk will be roughly 45-50 minutes. Sergej has promised me, and before he starts, I'll very briefly introduce our speaker today, which hardly needs any introduction. Sergej Demokritov. He is a professor at the University in Münster, and originally he comes, like so many smart physicists, from Russia. So he did a PhD at the Kapitsa Institute in Moscow, and then he did the habilitation in Kaiserslautern, which is one of the hosts of this series. And since 2004, he's been professor at the University in Münster, and he leads a research group that focuses on spin dynamics and quantum thermodynamics of magnetic structures. Of course, he's many papers on various aspects of spin rates research, and one of the people that did a lot of work on magnonics. And for instance, there's honors, there's a whole list, but one thing that we picked out was that he was included as the Scientific American 50 annual list as research leader for creating room temperature Bose-Einstein condensate in 2007. Okay, so it's a great pleasure that I hand over to Sergej, and I'm looking forward to exciting updates from this exciting part of science. So Sergej, please go ahead and share your screen.
Yes. Okay, no.
That looks perfect. Please go ahead.
Hello, everybody. First of all, I would like to sincerely thank the organizers for giving me opportunity to speak here. And I will be speaking today about Magnon Bose-Einstein condensate. And I would like to acknowledge a lot of people with whom I was working on this topic. First of all, people working or have been working in my group in Münster. Cooperation with Gennady Melkov from Ukraine was very important for this research field. Also, theorizing in Andrei Kirilyuk helps us to develop heterodyne, a very sensitive spectroscopy tool. Theoretical support from Natasha Berlov from Cambridge and Andrei Slavin and Vasil Tiberkevich and Vladimir Safonov and Boris Malomed are really very, very important. I will be talking today of magnons, and since we are talking here I'm talking in the seminar, I expect that people know what magnons are, or spin waves are. But I'd like to emphasize one important thing. First of all, creation of magnons change the longitudinal magnetization of the system. 1, 2, 3. But the magnets carry out transverse magnetization. And Bose-Einstein condensation is in really synchronization of the transverse magnetization. And the cartoon you see here is really shows us how the Magnon BEC looks like. And you see that spins are precessing, and although they are not all in phase, but they are coherent, and you see that it's just because the condensate correspond to the wave vector, which is not equal 0. Few words about atomic BEC. I've shown this slide just to emphasize a very simple thing, that according to Einstein equation, it is shown that the critical temperature is inverse proportional to effective mass. And since the mass of magnon is much smaller than the mass of atoms, we should expect that the critical temperature will be much higher than in the case of atom. And from point of thermodynamics, the BEC took place when the chemical potential of the system, which depends on temperature and density of the particles, reach the minimum energy of the particle. And there is two possibility to do that. First, to change the temperature, cool the temperature, and that reduce the temperature, cool the system, and increase the chemical potential. Or what we are doing, increase the density of particles. We will be talking about magnets existing in yttrium, iron, garnet, especially in films. What is important that the spectrum of dispersion of spin waves is determined by 3 energy contributions. The first is a trivial one. It's Zeeman energy, shown here as a green. Since it's not interaction between magnets, it's just single ion energy, so it has no wave vector dependence. Then there is a dipole interaction, which due to confinement in the field has such kind of unusual behavior, shown yellow, and the standard exchange, parabolic exchange, which always exists in ferromagnets. The total dispersion is shown here in red, and you see, as I already mentioned, that the minimum corresponds to non-zero wave vectors with the wavelengths which is in the scale of 1 micrometer. What is important? The energy, the minimum, is just above the Zeeman energy. And here I have calculated the contribution to the energy, the minimum. You see that the Zeeman contribution is about 2 gigahertz. Oh, sorry. The dipole-dipole interaction contribution is about 150 megahertz. Of course, it is for given magnetic field and the thickness of the field, but the orders of magnitudes are more or less the same. And the exchange is just 15 megahertz. It means that in the minimum of the spectrum, magnons are dipole-dominated particles. It will be important for our later discussion. As I said, our approach is rather simple. We increase the density of particle, and to do that, we inject magnets using parametric pumping, and after that, we observe or investigate magnon gas using brilliant light scattering spectroscopy with the time, space, wave vector, and sometimes even phase resolution. What is important to notice that in the classical way, Brilliant light scattering is used to determine quasi-particle with well-defined k-vector. You have incident photons, you have scattered photons, and the wave vectors of these two photons define you the wave vector of the particle, in our case Magnon, and by changing the scattering angle, you can change these wave vectors of interest. We instead already in experiment by using wide angle optics perform physical integration of the spectrum, and on this way we obtain not information for one wave vector, but we obtain information from a given interval of wave vectors, and therefore our signal, our profiles, which I will be showing later, represents nothing else as the population function of magnons multiplied by its density of states, which was of course calculated keeping in mind the restrictions of accessible wave vectors in BLC. And already in this picture, you see that since we have minimum at non-zero k vectors, there is a degeneracy. There are two wave vectors, two minima, and that will be also important for in our cases. Well, let us start. Let us remind you a classical experiment which results in discovery of BEC. We start pumping and observe the Magnon gas. The black curve shown, which you probably even do not really see, gives us the population distribution of magnets over the spectrum after 100 nanoseconds. We observe. Then when we record the profile after 200, 300 nanoseconds and further, we see how the intensity grows. Well, it's not surprising because we inject in magnets, but it's also surprising that we can calculate. It's not also, but it's what's surprising that we can calculate the distribution of magnets, which correspond to the maximum value of chemical potential, which cannot be larger than the minimum energy of the system, and this distribution correspond to this olive curve. But experimentally, we see that with the time being, the intensity here close to the minimum of the spectrum grows and grows. What is even more surprising and more exciting that while the intensity here grows, the intensity of the density of magnets away from the minimum energy is not changing. It means after some period of time, almost most of the injected magnets are collected at minimum of frequency, which is expected from the scenario of Einstein. And it's also understandable if we reduce the pumping power. It means the rate of injected magnets will be less. The behavior is completely different. We saturate the distribution is saturated below the critical value, and so we do not observe the condensation. So if we now come back to this curve, and if we calculate the difference between the experimentally observed data and this Bose-Einstein statistic curve, we will see the following things. We see a peak, which is located near the minimum value, and that is this is Bose-Einstein condensate. Although you will see here that it's not very narrow, but I will be talking about. Nevertheless, this is a clear indication of a transition, and this transition is here. Is important to notice is synchronization on transverse magnetism. You see here the title of our paper in Nature in 2006. And already in this time, as I already said, it was clear that we have two minima and experiments with possible observation near one or another minimum told us that this is the case. The condensate is created in two minimums simultaneously. But what I'd like to say that immediately after publishing our paper, is better to say in the same issue of Nature, there was a paper from, or note from David Snook, who asked several questions connecting with this discovery. And his main question was, is it the right term to use to describe this phenomenon? 1 or 2 years later, another paper came out where Tupitsin and co-authors questioned stability of the condensate there. And that were the important questions which we have to answer to our scientific community. And let me cite the people that, for example, David Snook wrote that direct evidence of spontaneous coherence in solid has been hard to come by. In our paper, we demonstrate a build-up of population of magnets in the group set, but present no direct text of coherence. So, therefore, for several years, for us, it was obligation to answer important question. What is the temporal coherence of condensate? What is the spatial coherence of the condensate? In addition, David Snook wrote that the coherence should be spontaneous. That fact is essential. Many systems can be coherent and driven another source. For example, he gives example of loudspeaker who produce coherent phenomena. Therefore, for us, another question was, is it coherence spontaneous? Is the coherent condensate created as a result of thermalization? And in paper of Tupitsin, they presented a reasonable question. They said, okay, in experiment reported so far, the intermagnet interaction were actually attractive. And for this case, the BEC should have been unstable. And the fourth question, which was for us very important and fundamental question, what is the mechanism of stabilization of the condensate? Because in experiment, we see that the condensate is stable. Well, the simplest was the thermal coherence. And again, in 2006, in this Nature paper, we have already given the estimation that the line width which we observe is instrumental line width. And in any case, the intrinsic line width of the condensate, in any case, below 50 megahertz. 2 years later, we reduce this limit by 1 order of magnitude and show that it's below 5 megahertz. And finally, it took a little bit more time by developing a special heterodyne spectroscopy, which I will not go into describe in detail. Just let me say that the frequency resolution of this technique is 200 hertz, not megahertz, not kilohertz, 200 hertz. We were able to determine intrinsic line width of the condensate, and it was 800 kilohertz, and confirm that really the effect which we have reported in 2006 represent a very coherent object, at least coherent in time. To investigate spatial coherence of condensate, we performed experiments with K resolution, and we record how the condensate is formed in the K space. And here is a experimental data where we K vector, we measured with K vector resolution and the time resolution. What we can see that injected magnets collected in one point or in one area or in the K vector, and with the time, this distribution becomes much narrow. We also performed space resolved measurements, and we have shown that if we scan with very good spatial resolution, much better than it was before, with sub-micrometer resolution, we can observe oscillation, spatial oscillation in the condensate density. And this is connected with the fact that we have two condensate, or two components of the same condensate, which correspond to opposite wave vectors, and their interference gives us such interference picture. And by analyzing this picture, we were able to confirm that the coherence length is about 40 micrometers. That is about coherence. What's about the thermalization? Well, what should we do? We should just look what the experiment tells us, and we perform experiment, and we have continuous pumping, and we see what happens with the Magnon distribution with the time. And what we see, here really that distribution, we pump our magnets somewhere here, the K vector somewhere here, since the K vector of the pump magnets is beyond the interval of our BLS. Therefore, we do not see such a strong peak in this frequency. But what you see here is just a small rest of this peak. But what we see then, that first the distribution increase in higher frequency, and then its wave flight goes to the lower frequency. And this particular experiment was performed at a relatively low pumping power just on the onset of the condensation. Therefore, we see that it happens rather slow. 250 nanosecond is the thermalization time, and the relation and the overpopulation of the lowest state is not so high. But if we just increase the pumping power by a factor of 2, we immediately see that the thermalization time becomes very much shorter, and therefore it is not easy to get such nice cartoon of the data. But and also the overpopulation becomes much stronger. So on the scale, you do not see anything beyond these people. So this tells us that really the coherence is spontaneous, because it happens over many Magnon scattering events. Even more, you can also do experiment with pulse pumping, and in here you see the results of the experiments when we inject magnets intensively, quite a lot magnets, but during very short period of time, to 20 nanoseconds, and then we observe what happens. What we see first of all that these magnets which we observed, as I said, it's not a real intensity, it's just a rest, because the sensitivity of BLS for these particular magnets is rather poor. But nevertheless, we see that after another 20 nanoseconds, this peak disappears, and then the distribution slowly goes down to the minimum frequency. And we also see that narrowing of the distribution with time is observed. So it is another confirmation that our coherence is spontaneous. The fourth question I have already mentioned is, what is the mechanism stabilization of the condensate? In fact, that was really amazing. It was surprising that it is well known that the Magnon interaction for this geometry is attractive, and one can observe a lot of phenomena which, based on Magnon attraction. For example, we are ourselves observe solitons in these systems, and if one asks theoretician, they say yes, it's attractive. Here in the very small wave vectors and the high wave vectors, it is very strong. Close to the minimum, it is very weak. It is weak because there's just a contribution from the dipole, and exchange energy is weak, and the interaction is due to dependence of magnetization, for example, or exchange constant on the Magnon density. And since the main part of the energy is determined by Zeeman energy, it is not surprising that it is weak, but still it's attractive. And we were asking ourselves what is in reality. And we performed very sensitive experiment with very high resolution, and we measured the thickness, the energy of the condensate with high frequency resolution. You see here, there's the frequency change here is 1 or 2 megahertz. So using this technique, and what we see really that if we increase the pumping power, first it's the frequency goes down, and it is correspond to the data which we have seen just before. But then if we increase the pumping power further after the threshold of the BEC formation, a clear increase of the energy is shown here, can be observed, and it means that the interaction between magnets is repulsive, because as soon as we have higher density of magnets, and if the interaction is repulsive, the mean energy per particles should increase. And simultaneously, Andrei Slavin and Vasil Tverkevich developed a theory which came out of standard Magnon interaction theory, because in standard theory, one considered so-called self-interaction. You take some magnets and increase their density and look how the energy is measured. But they came further, and they said, okay, there is degeneracy. There are two minima, and it means that magnets with the same energy but belonging to the different minima should also interact, and that interaction results in repulsion. So that was one of the questions. And later in my talk, I will show that there is another extrinsic mechanism which also responsible for repulsion, but here I show you this one. And then I would like to show you some our recent experiment where we take advantage of a recently developed way to control condensate by inhomogeneous field. All the experiments below were performed in uniform field. But here we change experimental conditions, and we put the sample on dielectric resonator, and on the top of the sample, on the knees of the sample, we put microstrip, and and the current flowing through the microstrip, create local inhomogeneous magnetic field. And we can do with this control line whatever we would like. We can just let DC current flowing for forever. We can put pulses, positive and negative. We can put a sinusoidal signal. And on this way, we can control locally the field, which is nothing else as the chemical potential of the condensate. Well, it has a main contribution to chemical potential. And if, for example, we applied radio frequency modulation, you see what happens. Here you see space and time resolved intensity of the condensate. And what you see here, this position is a position of the control line and then in some moment of time, we switch on the radio frequency signal. And you see, well, you see that first of all, the intensity of the condensate on the top of the line is oscillating, which is not surprising. But what is really surprising that we see some waves which propagating out of this control line. And if we calculate delta t and delta z of the propagating wave, we can calculate its phase velocity, and this is nothing else as omega over k. So this is the first experiment which shows that we can create in this system using such simple approach. We can create a second sound. There is a few, I'd like to say a few words why we call it second sound. Well, in analogy with a second sound in helium or solid state phonon, when one has, let's say, solid state, and one has made of atoms, and if atoms are oscillating, by quantization of this oscillation, one creates phonons or first sound. If now we have a phonon population, and then we create inhomogeneity in phonon density, and this inhomogeneity propagates like a wave, we call it second sound. Here is exactly the same story. We have a ferromagnetic field which consists of spins. If spins are rotating, we create magnets. And now we have Magnon distributional, and then we modulate the density of magnets, and we see disturbance of this density, which propagates like a wave. Therefore, it's Magnonic analog of second sound. We performed these experiments with a given frequency, and then measured using the pictures similar to what I have shown. We can determine the K vector and damping, and we have shown that the K vector is complex. It has real and imaginary powers. That means that the wave is dissipative. By varying the frequency, we can determine both real and imaginary part of this wave, and it is shown here. Very interesting. This sound is observed as below as above the transition point, and this is also predicted by the theory. There is also second sound above the helium transition, but above or even close to the lambda point, the second sound is damped. So the real undamped second sound was observed only at a very low temperature, where the normal component, the density of normal component is very small. And if we compare this our experiment with these experiments, we might say that whatever we do, we are very close to the transition point, because the density or the number of magnets in condensate is much smaller. In different experiments, 1% or 1 per mil with respect to all magnets existing in the system. But in the theory which describe this second sound, developed by, as I said, Vasil Tiberkevich and Andrei Slavin, they imply, which is very reasonable, that there are two relaxation rates connected with the relaxation of energy and relaxation of momentum. And then if one writes correct equation, one get the proper dispersion, which nicely describe our experimental data. Our experimental, and these lines correspond to the results of the theory of Tiberkevich and Slavin. Another possibility to use the control line is just to let constant current flowing through it, and observe how the condensate is redistributed in space. Really, if we create a current in such a way that the local field is reduced with respect to the outside, we should expect that the density of condensate in this reduced field is increased. As a matter of fact, if it will be an ideal gas without any interaction, we should expect that the entire condensate, later or earlier, collected close to this control line. And that was for us interesting to see what has happened. And you see here an experiment, as I said, and here everything, this is quasi-equilibrium experiment. We switch on field, switch on pumping, and we wait for forever. We can repeat this experiment for several days. As a matter of fact, the picture I have shown with interference due to rather small contrast, we have to collect this picture over 2 weeks, and it tells us that the phase locking between two condensates is very robust. Okay, what we see? Well, as expected, if we decrease the density, the magnetic field locally, we see how the density increase with respect with the calibrating curve, which correspond to just a plane profile of the field. If we increase the field, we also see that the density is decrease, and it is clear that we can create either potential trap or potential heal, and the condensate is trying to find the lowest place with the lowest chemical potential that explain this behavior. And if I plot the stable density as a function of the depth of the trap or height of the heel, you see this dependence. For heel, we see exponential dependence, which is more or less predictable for ideal gas. But for negative data, it means for traps, we see deviation from this behavior, and I will address this deviation a little bit later. What we can do to understand what is going on, we can also make a space resolve measurements, and we can measure not the maximum density as here as shown in the previous slide, but the entire profile of the condensate density, and we see that in effect we have a profile. What is interesting here? This gray rectangle corresponds to the control line. It means that the magnetic field is more or less localized close to this line, but the peaks we have observed is much broader. Moreover, what we also see here that for the negative delta H, which correspond to the trap, positive delta H, which correspond to the field, we have opposite behavior. To understand that, we first tried to write Grove-Pitayevsky equation, and take into account that there is interaction between magnons, and this is interaction term. But then we realized that that our system has many states, and since the trap is rather broad, relatively broad from the quantum point of view, we don't have nice separation between states, localized states in the trap. Therefore, we have dissipation. And instead of this non-dissipative equation, we have to adapt it to include here dissipation. And by doing that, we came to the quasi-classical flow equation, which is shown here. What we have here, we have three constants which describe different phenomena. First is this J, which is correspond to this J. This is interaction. Here we describe relaxation of the gas, because if we switch off the pumping, we will know that the condensate dies out, and therefore we should take it in account. But what we introduce here is a mobility, and I will explain you why it is important. So it means that we have to take into account that there is a lateral flow of magnets. And you see that in this equation, we have only two feed parameters, because tau can be measured separately without any trap, by just observing how the condensate died out from the without trap. Well, as I said, what is important? That that far away from the trap, we also see the influence. What is plotted here is normalized condensate density. Without trap, we will have a continuous, or more or less constant density, but here we have less than 1. It means that magnets from here flow here, and that is a very important experimental result that we observe here, transversal flow. And by fitting the data, you can easily do that, because two parameters mainly responsible for different things. The G responsible for the height of the peak, because it's clear without G we would have a collapse. If we would not have positive G, which corresponds to the repulsion of magnets, here there is some kind of simulation. You see how if we reduce G, how the peak grows, and for 0 G, now our calculation just diverges. So this is, and it's clear why the repulsion reduce the intensity, because the magnets do not like to be together. The repulsion pushed out the condensate out of trap. Whereas the mobility mainly defines the width of this peak and this behavior. So by fitting these curves with very nice results, we obtain the value of interaction, which happens to be repulsive, but also we obtain mobility. And from the value of the mobility, we can calculate the corresponding relaxation time. And this corresponding relaxation time was huge, 100 times larger than the relaxation time of the condensate density. And that is up to now for us a mystery, why it is so. To demonstrate pictorially that that we have this repulsive interaction, we made following experiment. At some moment, we abruptly switch off the pumping. And of course, with the time, which I have already noticed, the condensate density decrease. But what we observe here, it's again normalized density in absolute value. The red curve is much smaller than the blue, which is much smaller than the black. With the time, the total density decrease dramatically. But you see that with the time, the profile becomes narrow and narrow, and we see how something press the profile to the center. And this is also reflected here. If we take one point here and measure the time dependence, we see that at z equals 0, we have slow changes, whereas somewhere here we have very fast changes. It means that condensate is flowing from one point to each other, and this is a clear indication of the repulsive interaction. For high densities, the condensate was extruded out of trap, and then if the density becomes smaller, the interaction is not so important. The profile becomes to correspond to the field profile. The another story. I probably not be holding my promise to be ready in 45 minutes. Probably another 5 minutes I will take. I'm sorry. We can also use this control line to create to separate two condensate. In all experiments we were talking about before, we have degeneracy. We measure the total density of the condensate, and this was a result of contribution of two condensates. Now, if we increase by using the pulse, we increase locally the magnetic field and bring the condensate from this minimum to here, we see a rather interesting possibility. Since the field outside the control line corresponds to this dispersion, the condensate from here can easily relax to here. And it means that from the condensate from the hill just roll out from this place and comes into motion. What is also interesting that since the curve here is strongly asymmetrical, the velocities of these two clouds will be different. What is also important that for two minimum, the signs of this velocity will be opposite. If, for example, this if one for minus k, the fast motion will be in to right, for the k plus, the fast motion will be into left. So it means it gives us possibility for a spatial separation of the condensate, and it is experiments tells us that in reality it happens. So we see that in one direction, by making experiments with resolution of k, making the experiment sensitive close to the one minimum or to another minimum, we see how to this minimum propagates fast and slow clouds propagates in opposite direction. And if we follow this propagation, we can see how these clouds are separated here. And also we can calculate the velocity of these clouds based on this Magnon spectrum. What we can do else? Well, we can do the following experiment. We can keep the pumping constantly working, and then in some moment of time switch on the gap, the trap. Sorry. And what we see is shown here in this graph. We see that the density becomes to increase with the time. It's exponential increase, and we know why, because in the gap the density at the end of the day should be larger than it was before. But in addition to this slow density, slow growth, we have oscillations. And I plot here different curves for different depths of the curve, but it's here we have not the time, but reduced time. So I multiply by time by Larmor frequency corresponding to the depth of the time. And in this scale, we see that the exponential growth of the density is the same. It means that the time, we have here three different frequencies of time parameters. Time is inversely proportional to delta H. We can also measure the oscillations frequency, and it's in a frequency range of several tens or 20 megahertz, and it's proportional to the square root of delta H. And we also show the damping of the oscillations, and surprisingly, it's constant. And probably not surprisingly, because it's already here. It's clear that these oscillations by small delta H is strongly damped as here. And since the damping is independent of the gap depths and the frequency increase, it is not surprising that these oscillations are better to observe. But already in this picture, it is clear that oscillation frequency is not proportional to delta H, because if it will be also proportional to delta H, so on this scale, it will be the same. And I here put the mark on the first and the fourth oscillation, and you see it's not the same. It means that the dependence is different. And to understand what is this oscillation is about, we again took advantage of our space resolution and measure space and time profile of the oscillation. And what we see, that is by no means oscillation between the gap between the trap and outside, but this is oscillation inside trap. And we can imagine this this oscillation as a redistribution of the condensate density within the trap. And this is nothing else, as I would have here, but when I put water in this glass, we see that there is oscillations when the water flow into the glass. This is exactly what we observe here, and that gives us possibility to say that condensate demonstrate properties of Magnon liquid, because it's compressible, finite compressibility with repulsive interaction, and show such kind of oscillation. To understand and to make some toy model, we took into account that by changing the trap depths, we also change the curvature of the bed of the trap. And then considering these oscillations by the as a harmonic oscillator, we are able to reproduce these results. Better to say two harmonic oscillator, because you see here that after we have here maximum, we have two maxima outside close to outside the center of the peak. So it should be two parts of the condensate which oscillate in outer phase. Probably these are correspond to components of the condensate. We are going to perform K-resolved measurements to confirm or to deny. And I'm almost on the end of my talk. I'd like to say a few words about a very general question. What is the main difference between Magnon BEC and the atomic one? And for that, I have to go back to the basic of quantum mechanics. If we have a state, eigenstate of Hamiltonian, we can write the time dependence of the wave function as multiplication with this imaginary exponent. And this imaginary exponent has phase, and this phase change with the time, but this is not observable. This is a basic of quantum mechanics. Just because, for example, that the energy here comes, that we here have the energy, not the energy difference. It means that the time dependence of this phase depends on the definition of the zero of energy. And this is also true for specific spin states. If we, for example, consider spin 1/2 and consider plus and minus states, pure states, we have the same picture. We have here time-dependent phase, which is not observed. But if we take arbitrary spin states, which as a linear combination of spin up and spin down, we will have something more complex. We will have, well, parameter in addition to initial phase difference, which correspond to the just phase of the linear combination factors here. But if we would like to follow the time dependence of the states, we will see something dramatic. We will see here that we have here a phase, time-dependent phase, which is now observable. And exactly this phase tells us in what angle in this particular moment, for example, if you have a condensate with large number of spins, it is well defined, tells us as the position of the magnetization of condensate in a given time. So, in this means the frequency and phase of our condensate is the phase difference between two quantum mechanical states, and therefore it is observable. Contrary to the atomic BEC, where the phase is not observable, and the only way to create ensemble of phase synchronized atoms, it's one of the way is a BEC. Here, since the phase is observable, we can also control. And from this point of view, it's just a standard ferromagnetic resonance has the same property as the condensate. And from this point of view, one should be very, very cautious when talks about supermagnonics, because from the basics of quantum mechanics, our condensate is very similar to the wave packet, coherent wave packet, which we create using microwave antenna. Of course, the main difference is that since this condensate is created in the minimum of the spectrum, it is not propagating, whereas all others are propagating. Okay. And mein Zetron-Sensor Cartagena Sedelendum, I'd like to say a few words about spin current and spin waves. When we describe magnetic dynamics, we have Landau-Lifshitz equation, which tells us that the time derivative of the magnetization is determined by some torque, and this torque is determined by effective field, which takes into account all possible interactions. If we'd like to apply spin current approach here, we should substitute this torque by a gradient of another value. Is that also possible? No, it is not possible in all possibilities. And in this paper, for me, it's the first paper which addressed this point. It was shown that it's possible for pure exchange model. And the authors, Cherkonyak and his authors, they wrote this equation which described the spin current for magnetic dynamics. And let me emphasize that it's true only if we have pure exchange model. If it's not, and it's similar to any physical system where we introduce the current. We can only introduce the current if we have conservation law, continuously equation. And if it's not, we cannot introduce current. In general, angular momentum is not conserved in spin system. Therefore, even if we don't have a spin-lattice coupling, magnetic dipole interaction results in spin-lattice coupling, and therefore it is not possible. Especially, it's obvious if we consider our condensate. In fact, the equation for plane wave tells us that the J is proportional to K vector, and that means that if we apply the spin current to describe our condensate, we should say that here in the minimum, there is a continuous persistent spin current proportional to this wave, which is obviously not the case because the cloud is not moving and the velocity is zero, it is at rest. And let me remind you that these magnets are dipole dominated. Therefore, any description of these magnets using just such a simple equation with the spin current is questionable. Now, by this, I am at my summary. I have shown you that discovery of BEC 15 years ago opened several fundamental questions, and it takes us several years to answer them. And now the coherence properties of condensate are well established, at least from the experimental point of view. We can also observe second sound. And in general, introduction of local inhomogeneous magnetic field as a stimulus opened a lot of new opportunity for investigation of spatio-temporal dynamics of condensate, which now it's clear show properties of Magnon fluid. And since magnons of the condensates are dipole dominated, the attempts to describe the condensate using spin current approach are questionable. I will say. Thanks. I'm fine. I am done. Thank you very much for your attention.
Thank you very much for your talk on spatial-temporal dynamics on Magnon Bose-Einstein condensates. I do see a few questions, and I would like to Daniel Komsky to first unmute and talk and ask his question.
Okay, very nice story. And I have actually two related questions, simple but related questions. Is it known that Bose condensation very strongly depends on dimensionality of the system? For example, for simple quadratic spectrum, it formally exists in ideal case for 3D, but not in 2D, for example. So question number one, what is known, what becomes of all the story in films, for example, in your material? And second, question.
Yes.
Right away, maybe just two questions, they're related somehow. And the second question is that Bose condensation also depends very strongly on the dispersion relation of corresponding particle excitations. For example, for quadratic excitation and for linear, it might be very different. So is anything known about ideal antiferromagnet in which spectrum would be linear? So these two.
Okay, thanks. Thanks for the question. First of all, I would like to answer the first question. Look, when we are talking about dimensionality of the system, we should think about scale of the energies. If you have, for example, quasi two-dimensional gas, you can call it two-dimensional if the temperature of your system is much smaller than the energy the system needs to jump to the next state, which correspond to the vertical motion. In our case, it is not the case. It's not true. In our case, we see that I have shown you just the lowest part of the spectrum, but of course we have in our films, we have perpendicular standing modes, and then which gives our system three-dimensional. And the distance to these perpendicular modes is in different films few hundred or few tens of megahertz, which corresponds, it's much smaller than the temperature energy. It means from the thermodynamical point of view, if you calculate the density of states or whatever you do, the system is three-dimensional, although for our case, for our description, we use a simplified picture saying that it's two-dimensional. This is the answer to your first question. The second question is, well, I do not know any results about the linear, because I have my problems with a linear dispersion, because if it's a linear dispersion, there is no gap. It means the minimum state corresponds to zero energy. And then, of course, we have possibility to consider, for example, if we consider the reorientation transition in ferromagnet or even in antiferromagnet, and we know that at the moment as the minimum energy of magnets goes to zero, we have a transition. There are people who describe this transition as the Bose-Einstein condensation of magnets at zero energy, but I'm not very happy to as a antiferromagnet in general are concerned. I'm aware of several publications where people claim that they observe BEC, but this I'm not convinced, because in this works people really make antiferromagnetic resonance, and they has no results about real thermalization. Everything which I have shown here, that it's really thermalization, that it's not just something which is David Snow called the loudspeaker, and that sound. Therefore, I'm very cautious about things.
Okay, thank you.
Next question is by Mohammad Hamdi. Could you please unmute yourself?
Yes. Do you hear me?
Yes.
Yes, I can hear you.
Okay, great. Very nice talk. I enjoyed it a lot. I just had a bit of confusion when you were comparing atomic and magnonic BEC. When you used the spin-1/2 to draw an analogy between the magnons and the atomic BEC. I wanted to ask a bit more explanation about that, because spin-1/2 is a fermionic description, and it doesn't fit to BEC, right?
No, it fit BEC. What is the point? Look, it has nothing to do with BEC. It has something to do with magnets and with quasi-particle itself. If you have an atom, as I said, the quantum phase of the atom is not observable. But if you have a photon or a lot of photons, yeah, and then you can determine the phase of this electromagnetic wave. The same is for magnets. We present magnets as precession, and the phase of the precession can be easily observed just by some experimental technique. So from the beginning, the phase of magnets, let me emphasize that the magnet is a quasi-particle which is created as a linear combination of two pure quantum states. The phase of each of these states is not observable, but what we call the phase of magnetic precession, it is not the phase quantum mechanic, it's the phase difference between two pure quantum mechanical states, and therefore it is observable.
Okay, I see. Then you use this spin-1/2 example to show the phase difference of two states.
Yes, I tell you just 1/2 just to make a pictorial illustration, because I do not want to spend half an hour making real quantum mechanical calculation for arbitrary spin. My main point is that, contrary to atom, magnon is a result or is described by the linear combination of two pure spins, and therefore and since this combination, these pure states have different energies, the phase difference between them oscillate with the frequency, and this is what we usually call the phase of the magnet or spin waves.
Thank you very much.
We have a next question from Pavlo Sukharov. Could you please unmute yourself?
Thank you very much for a nice and informative talk. So my question is, what are the most definitive signatures of the Magnon Bose-Einstein condensates that can be extracted from only time domain measurements?
From time domain measurement, the temporal coherence. If, for example, if you would have possibility, and we had this possibility, if you have your sample, and that was one of our, here. That was microwave experiments. We have our sample. We put an antenna close to the sample, and then we pump magnets. And unfortunately, I have no original picture from this paper, but believe me that in the beginning, the antenna was detecting nothing. And then, at the moment as the condensate was created, we have a jump of the detection signal 5 or 6 order of magnitude. So we have a noise which we were able to detect, and then it was many orders of magnitude signal, and that was based on this experiment. We were able to determine this this line width, or give a limit. The problem with BEC, for this particular BEC, is that its K vector is the wavelength is about 1 micrometer. And if you'd like to have linear detection, you cannot do it simply. So in our experiment, we had some detection where we detected a pair coherent magnets with the opposite K vectors, and therefore we have to introduce some additional channel. Therefore, the line width which we measured here was the upper limit. But in principle, I see no other way I see no way just for time resolved measurements. Or here for heterodyne results, we also made just time measurements. The idea was we flashed our sample with sequences of very short pulses and measure the Faraday magneto-optical, let's say, output. And in the moment as we have seen the transition took place, we see a huge signal. And by sending this signal from the photodetector to spectrum analyzer, and by tuning the magnetic field, that the frequency of the condensate was close to the integer of the frequency of our flash, we saw very slow precession, and that therefore we were able to improve the sensitivity down to 200 Hz. There are a lot of possibilities to investigate if you just have time resolution.
Thank you very much. The next question is from Jamie Marino. Jamie, yes. Can you please unmute yourself?
Yes, thank you so much, Karin. So thanks again for the nice talk. I come from a little bit different community, but your subject is anyhow inspiring. So my basic question will be if you can realize a time crystal with Magnon condensates, and in order not to sound cryptic, let me explain what I mean.
Yeah, please.
Forgetting about
I do not understand what you mean.
Yeah, exactly. Let me clarify it. Let's forget about damping for a moment. You have the frequency of these oscillations, just to clarify those that you were showing in the last part of your talk. Can you generate stable frequency of oscillations? By stable, I mean that in a certain range of parameters, you always get the same frequency as a response. In some sense, it's rigid. You cannot tune it. So sometimes
yes, the frequency is fully determined by applied magnetic field.
So if I, let's say, have some impurities in the medium, if I have some disturbances, if I have some additional, let's say, inelastic processes, is there a range of weak perturbation in which I really get exactly the same frequency when I do this Floquet drive on the problem? That's if you want a question. Rigidity means this.
I understand. Yes, well, it depends on the accuracy you're talking about the same frequency. For example, if you look in this picture, which is occasionally on my screen, you see that the condensate has a finite width. And,
yes.
Even more, we see that it's asymmetrical. For higher energies, it has a tail, and for lower frequency, it is much narrow. Oh, not much, but several tenths of percent narrow. And we interpret that, for example, as the existence of thermally excited, or for some reason excited, second sound waves, which just propagating on the top of the condensate. From this point of view, of course, the frequency of the condensate is not so stable that you can make atomic substitute by condensate atomic clock. On the other hand, we also observed in some pictures that impurity can disturb spatial coherence. But as the temporal coherence is concerned, I believe that it is if on the coherence length of the stage of the scale of coherence length, the density of the impurities is more or less constant, is averaged, and is similar to, it's called exchange narrowing. So they will not disturb temporal coherence. So to be honest, I do not know what is the mechanism which determined from the theoretical point of view the intrinsic line of the condensate, because it can, well, I can hardly imagine that it's connected directly with the lifetime of single magnon, because in the experiment I have shown here, it was a continuous CV experiment. We compensate the dying out of the magnons, and the density of condensate was stable. Nevertheless, it is has a finite width. I can imagine that it's due to the fact that condensates is under influence of continuous flow of magnons which are condensating. And I just from my feeling as experimentalist tells me that this continuous flow of non-condensed magnons which are condensing now partially increase the line width of the condensate.
But this, just a very quick point, so this line width that you are showing in this plot, is this a fine-tuned point, or do you have a broad region of parameters in which it can remain very sharp?
Well, yes. Well, you know, the parameter space is many dimensional, and
sure.
I cannot say that we have found the best point, but believe me, we tried to find. And if I present here some result and said it's a typical results, you know, well, it's probably the best results we were able to obtain, because nobody shows bad results. So from this point of view, in some sense, yes, this is the optimum place. Because you look, we have possibility to, for example, to vary the pumping frequency and the frequency of the condensate. And this is a very not clear question. How should we make the difference between them? If we make it too large, the magnons, I have shown you how they propagate from point of pumping to the bottom of the spectrum. They just died out on the way. However, if we make it too close, the influence of primary magnons, which are not coherent primary magnons, and if we have strong interaction of primary magnons with the condensate, it's also make the coherent properties of the condensate worse. So we were trying to find the optimum, believe me, and these are results at optimum.
Okay, thank you. Thank you so much.
Thank you. The next question is from Ali Reza. Ali Reza, please unmute yourself.
Yeah, thank you very much for a nice presentation. Just I have two nice questions. One is about the stability. Already from atomic BEC, we know that even in the case that we have attractive potential, we can have metastable BEC if number of the atoms are limited. In this case also, I think the number of the magnons anyway is quite limited. And then I'm wondering that, is there really any problem that we have attractive magnon interactions, but still have BEC because of the same reason that we have the BEC, metastable BEC in atomic case? And yeah, maybe you can first go through this one.
If I correctly understand your question, it was acoustically not very good. That what happens with the gas? What happens instead of BEC if one has attractive interaction? Is it
yes.
correct?
Yeah, because in atomic BEC we have.
The answer is simple. As I said, if you have magnons with attractive interaction, there are a lot of scenarios, but all these scenarios predict that you have condensation in the real space. So if you create, for example, in real space, a cloud of magnets, if they have attractive interaction, and if you have, in some conditions are fulfilled, they create something like soliton or bullet, which is very localized in real space, and then a long-living object which can propagate or not propagate. But the main idea is that any gas with attractive interaction is unstable with respect, well, probably not any, but I don't know now some contra example, but I will be cautious and say many gases with attractive interactions are unstable with respect of collapse and creation some very small or object localized in real space. For example, there was magnetic polarons which are localized close due to interaction between magnons, spins, and conducting electrons. In contrast, if your gas, if particles in your gas have a repulsive interaction, one can think about first that this is stable case every time if you have some kind of fluctuation of the density due to repulsive interaction. As you see in our experiment, this repulsive interaction push out particles out of this region, and the stability of constant density in real space is again restored. However, another condensation is this Bose-Einstein condensation, where instead of forming just a gas with a constant density, the gas undergoes a Bose-Einstein condensation, where the density in real space is still constant if you have only one condensate, but the atoms are condensated in K space. This is two competing scenarios.
Okay, thanks. And then just another question is, before your experiment in 2006, with the pumping of magnons and BEC, it was some experiments, very old experiments with the BEC of the magnons, but in the equilibrium case, they had the easy pairing or quantum antiferromagnet, then tuned magnetic fields. How different are?
Well, you know, as I told you, there are some papers. For example, many years ago, I don't know whether these people are still claiming that they observe of BEC. People were investigating magnetic properties of platinum cobalt alloys, or that is BEC, but again at zero energy. that is, I cannot understand.
But this means that there is no equilibrium of Magnon BEC then so far,
yeah.
at least. Yeah.
So it was cobalt platinum, quite small particles.
Okay. Okay. Thanks.
Another direction which I observe up to now is people investigate antiferromagnetic resonance, and they I'm not going to go into details, but in general, they investigate resonance and apply more and more power, and in some moment they observe something which is which looks like coherent state, correspond to narrow line and so on and so forth. Well, it might be, and I do not doubt that they were able to obtain the coherent state, but the question of spontaneously, the question as of thermal equilibrium between this condensate and rest of magnets is for me not clear. And I was talking to these guys many times, and they were not able to answer this question because, as I said, it's not my words, it's the words of David Snook, who is a big expert in BEC. The coherence should be, that the coherent spontaneity is essential. There are a lot of systems where you can create coherent state, but it's laser, for example, is a famous example. It's strongly non-equilibrium system, and well, again, it's a point of definition. If you say we call now BEC anything which happens, which gives us a coherent state using incoherent stimulus, well, then it is probably BEC. But up to now, I followed another definition written in the paper of Einstein.
Yeah, thank you.
So the next question is by a person who's named Alex. Alex, could you please unmute yourself? Okay, then maybe for the meantime, I'll read the question from the Q&A from Alexandra Sadovnikov, who says that he doesn't have a microphone. So his comment or question is, thank you for the very interesting talk. Regarding the spatial confinement and interference of BECs, can someone expect BEC in rotating or helical potential formed by spin configuration?